Hello, thanks Demetrius for the introduction. Today we're going to be talking about point-in-time data or mutable data in online inference. A quick intro, I'm Oren, I'm a software engineer, and I lead the work on Lemonade's machine learning platform. And Lemonade is a full-stack digital first insurance company driven by automation and behavioral economics. So let's start with an example business database or business application database. Let's say we have a users table with several columns and the transactions table with several columns as well. And we have many transactions per user. One day a new user is created or they add themselves to our table. Then that user makes a transaction. And finally, that user changes some of their data. Down the line, we decide to make predictions during transaction, online predictions during transaction. But the data in the business database has changed. We need the values at time of transaction to train on because we plan to predict at this time in the business process. This notion of a business point in time will seem quite obvious to anyone making online predictions. In our example, the date of birth was null during our prediction, but in our current database, it's now, there's a value there. So there are a number of ways to capture this point-in-time data. They're a little bit less relevant for this talk, but in general, we can do it in our application or in our infrastructure. In our application, we'll probably use events in some way. Or in our infrastructure, we can either use change data capture, maybe read the bin log somehow, or worst of all, snapshots, which are probably not granular enough, but we may all have them from some time in the past. So the point in time is a training data notion. I just want to reiterate, during inference time, we get the most recent values, but during training time, we need to recreate data identical to the one we would see at inference. And we'll see momentarily how we can benefit from this point in time. So let's try to define the business point in time as entity values at the time of a business process. Each point in time is dependent on a single entity's column. So for example, maybe if it was a transaction created point in time, it would be the timestamp of when the transaction was created. There's a different timestamp for each entity row. So maybe the transaction time would be different for each row, and then the users table, maybe we would even have, I don't know, multiple views of the same user for each transaction that they made for different timestamps. And most importantly, there are only several of these per business, which we'll see in a few moments how we can create some really cool applications from this. We'll compare the business point in time to snapshots just to make things a little bit more clear. So in the business point in time, there's a timestamp. The timestamp is from the entity. So like we said in the example, maybe when the transaction was created, and then there's a different timestamp per entity. When the snapshot, the timestamp is the same for the whole snapshot. Maybe we have daily snapshots, and this whole table is from August 1st, 2020. There are only several business points in time, and you only have to materialize each row once per entity per point in time, whereas per snapshots, you'd have many, many copies, and you'd materialize them depending on the granularity. An example of this is if our business was, maybe we have a SaaS business, we have new users sign up, they purchase something, and maybe they cancel their subscription at some point. And we want to make predictions only when new users sign up, when they purchase things, and when they cancel their prediction, when they cancel their subscription. So I've heard a lot of talk about abstract point in time or maybe time travel, and that's great for a lot of requirements. But we realized that our data scientists actually don't want the freedom to time travel anywhere, only to several specific points in time in our business funnel. And once we understood this, we were able to create abstractions for these specific or non-generic cases, which not only provided less room to make mistakes, but also resulted in some really cool applications. And let's look at several of these. So the first application is to monitor real-time feature service level indicators. So let's say our business application is streaming events and our feature store is processing them into a real-time store in a data warehouse. And then our business application, either through a model or directly, makes some synchronous request to the feature store to get features in order to make a prediction. This can lead to a race condition since the events are processed asynchronously, and this request is made synchronously. An example is maybe we're counting clicks, we're aggregating the number of clicks on some button, and we want to validate that our pipeline processes this aggregation correctly by the time we request the feature. So our feature store will maybe create a sum for these clicks that you can see. And we want to know that we've processed them on time by the time that we make this request. So how do we do this? In the green line, you can see is described the time between when we send the event and when the point in time when we actually synchronously request the features. And our goal is to detect race conditions which result in missing or outdated features. So the steps we've taken in our platform are as follows. Since the machine learning platform supports only a closed set of points in time, feature authors will configure the point in time availability per feature or when they expect a feature to be available. Then the business logic or our actual business application will tell the machine learning platform that a point in time has arrived for each entity where there's a point in time. The platform will calculate all of the features, but for some subset of entities and log them to the data warehouse. And finally, we'll materialize training data and compare that to the real-time inference data that we've created. So consequently, we can know the damage and make an educated decision, whether to synchronously put a feature, maybe not use the feature at all, or decide on any other solution. The drawback to this approach would mean that a feature needs to be productionized or authored before we can validate its correctness. It actually has to be in production, but it only takes several hours within feature authoring to know if a feature is available within a certain point in time, well before any model actually uses it or data scientist decides to use it in a model. So the next application of specific points in time is in communication. So with our stakeholders, the point in time is now part of the model contract, and the stakeholder knows when the model should be used. So this is decided on well before the model is created between the data scientist and the stakeholder. And this allows the consumer to know where in the business logic to use the model and the data scientist to guarantee its SLA. Within the platform, we'll have the point in time all through the machine learning lifecycle, whether it be in research, training and inference development, or monitoring. And this allows the platform to be consistent in its data quality guarantees. And finally, I think the coolest application is to be able to backfill legacy data in a sort of generic way by manually testing and backfilling per point in time. So let's say we're still creating these snapshots that we have from the past. We can now materialize or try to create data manually from these snapshots, or point in time data manually from these snapshots for each type of business point in time that we have. Then we can use our feature store, which obviously can materialize and works with time travel to materialize this same type of data from the feature store. Let's say we're materializing it for the past month, both from our snapshots and from the feature store. And then we can compare these rows from the legacy data to the current data systems. And we can make a calculated or an educated decision whether we want to backfill the data, whether it's good enough to actually train on, or to just throw away this data because it's not good enough, or do something else. But this only has to be done once because we only have several points in time, and not with every new use case. So this is a big time saver for data scientists. So in conclusion, if you're making online predictions, consider making the business point in time part of your machine learning platform. We don't have time for questions, but I will be on the Tecton Slack for the next several minutes or on LinkedIn or email. Thank you so much for your time.